Perfect. Nice to welcome you in this open space of the ITER building. And let's settle in. We'll have to do a little bit of coordination here with the ongoing review at the back. So I hope everything works out well. So welcome to the Design++ seminar series. We typically have 4 talks that cover machine learning, extended reality for architecture, engineering, and construction each semester. And as you already see, we are now at our 3rd talk for this semester. Very excited to have Menna El-Assady here with us to talk about intelligence augmentation and bridging human and artificial intelligence. I'll just briefly introduce Menna, and then we'll all enjoy the lecture. So currently Menna El-Assady is an assistant professor at the ETH, which follows a postdoc fellowship at the ETH AI Center. And it's impressive that relatively new started lab is already, we just discussed, almost closing to 20 people. Very interesting project that deal with human AI collaboration, exchange, and interaction. I'm always impressed by the projects where you are involved, that every project has a website and you can actually engage with the work and browse and see for yourself. So it's highly interactive, which would be, I guess, the topic of today. A lot of data visualization, a different kind of data visualization approach, the much needed explainability in AI, where we often talk, is it a black box? How can we look into that? So that's all research that you are doing, and I'm very excited to have you here today. So please join me in welcoming Menna for Design++.
Thank you, Anton, for the kind introduction. Thanks for the invitation, and thanks everyone for being here. I'm happy to talk to you today about intelligence augmentation. And as Anton already mentioned, I'm representing the lab Interactive Visualization and Intelligence Augmentation at the Computer Science Department, where we are trying to bridge human and artificial intelligence. So to start things off, I want you to imagine all of the complex problems our world is facing nowadays, and maybe all of the complex problems you personally need to solve in your day-to-day work. And I want you to consider maybe one problem, like climate change, and think about how we would usually approach addressing such complexities and kind of bringing people together to solve these wicked problems. So usually we would want to, for example, invite a panel of experts to come together. And these experts would kind of go around deliberating what their viewpoints is to solve a particular issue with respect to climate change. So some might mention things using slides, some might kind of use sketches or different types of mediums and different languages and so on and so forth to deliberate and figure out how do they share their opinions. They might also read the room and figure out people don't understand really what they're talking about, so they switch to a different way to communicate. And this human-human communication is very efficient, and it really relies on a lot of these human intuition aspects that we have developed over the years. Now, we've heard that AI has become very good at replacing humans in a lot of tasks. So what happens if we want to replicate the same experiment, but instead of human experts, we actually want AIs to take on this role? What will happen is that we will have a completely different system. It will rely on all of these AI models having very clear interfaces and doing a lot of very efficient communication, exchanging data and information. But clearly, AI communication does not rely on social interaction. It's not the necessary glue that brings together all of these AI systems. So now, say that we've experienced that some of the humans are doing the job really well, and some of the AI models are doing also a really decent job, and we want to bring them together. If we do that without any further approaches to kind of bridge the gap in communication, we will actually result in a lot of confusions and miscommunications. So one of the questions that I kept asking myself over the years is, how do we team up humans and AI agents to do efficient data-driven problem solving and decision making? So the goal of this talk is to show you some of the approaches that bring together humans and AIs with ways that allow us to do interaction and explainability through visual, verbal, and interactive interfaces. And the goal of all of this exercise is to have some sort of data-driven problem-solving and decision-making, especially for knowledge discovery. These two agents that we want to bring together actually could be imagined to kind of fill a spectrum of intelligence. Some aspects we want to kind of keep using in terms of the AI's capabilities, such as the search power, the data storage, the computing power, and so on. But for humans, we want to actually retain their understanding of semantics, general knowledge, and perception that are still very uniquely human. So for every single problem that you kind of imagined nowadays in your own work, you might have tasks where you still want to do them completely manually. You might have other tasks where you actually want to automate the entire thing because you've realized that AI is much more efficient. But you will have some problems where you want to have a mixed initiative between these two agents, some where you want to have full automation, but ask the human when you need them, human in the loop, and others where you want to have fully manual analysis and ask the AI when you need it, or the AI in the loop. So this collaborative human-AI interaction for problem-solving decision-making is what we dub intelligence augmentation. And here, the main principle is for every single task to try to figure out what is the minimal feedback that we can get from each of these agents to maximize our gain for the actual task that we're trying to solve. So in my lab, we try to figure out how do we design effective and empowering communication interfaces for human-AI interaction and collaboration. And in order to address this problem, we actually define 9 different research areas that allow us to tackle this problem from different angles. If you're interested to learn more about these research areas, they're available on the website. But for today, I actually will focus on these 5 here. And I will tell you a little bit the questions that we ask and a couple of these approaches that we try to take to tackle human-AI collaboration. So the first area is to try to figure out whether we can distill some sort of generalizable design pattern when it comes to workflows that consist human and AI agents. And here we need to cater for different diverse stakeholders, task complexities, contextualizations, and different environments in which this happens. So in some of the work, we try to figure out what actually happens when we try to break the trust deliberately between these two agents. And also, how do we evaluate human-centered machine learning? What are the approaches that the community has taken? Are there any general patterns? We also try to figure out if we want to break down this collaboration aspect, what are the different dimensions that people keep reporting on? So for example, agency, interaction, and adaptation are dimensions that people kind of keep repeating. To give you an example of some of these patterns, let's consider a problem in which we have a black box model that takes in some data and basically tries to sort this data into different topics. These topics can be true in that context, but maybe we have an expert that thinks that the topics that should be represented in a particular analysis should be completely different. So how do we bridge this human-AI alignment in some way that basically allows for people to externalize their knowledge and give feedback to the model, but also to ask for efficient feedback from the people? In the most primitive way we can put it, we can maybe design a linear intelligence augmentation workflow where we start with the data, train a model, get an output, and just get some user feedback. This is actually not that efficient. So one thing that we could do is instead of training one model, we can train multiple models. So we can train 2 different models and allow them to compete for the satisfaction of the user. And instead of asking users whether they think the output of one model is good on a scale from 1 to 10, we ask the users, do you think this model is better or that model? This is a cognitively much better task to actually address and also gives us something that is quite learnable for the model. So for example, we can use reinforcement learning to train a model to progress in that way. For the particular task that I gave you in topic modeling, for example, we can present them with a document snippet, tell them 2 different outcomes, and let them choose using a slider. And in the background, we run a very complex machinery using reinforcement learning to try to figure out what would be the most aligned representation to the human understanding. But in other tasks, we might have expert users who can override the data and the model output. If you have an expert that maybe worked in a particular domain for 30+ years, we could maybe start a workflow where we give them the data, let them generate outputs, and then train the model based on that interaction directly. So this is a workflow that we dub machine teaching rather than machine learning, where the human teaches the AI. And in the same problem of topic modeling, we might have an interface where we let people move around different concepts on a high level, and in the background, we try to learn the connections between these concepts that would kind of generate a process that gets from the documents that we have into these high-level concepts. So this is the first research area where we're looking at workflows, but in order to actually establish these workflows, we need to figure out how do we explain model decision-making from the model to the human. So in explainability, there are lots of challenges, starting from the lack of benchmarks to different disagreements and different XAI models and so on and so forth. So we really need to figure out how do we systematically explain model decision-making. For that, we contribute, for example, different frameworks that try to bring together different explainability techniques, but also we try to figure out, can we break down explainability in such a way that we actually do explanations onto a level that humans actually want to see, meaningful chunks of information that are conceptually aligned with our understanding of the world and not just with the model's understanding of the world. And we do that for multiple different data sources, such as text, time series, and others. But for now, I want to give you one example in which we do an architecture-level explainability. And in this case, architecture refers to the model architecture. So what I will show you is a quick video of a tool that we created that starts comparing multiple different model architectures. And if we like a particular area, to explore it further, or if a particular area is causing a problem, we can dig deeper from this multi-level view all the way to a single neuron and look at its behavior. So over here, we're starting with these different models. Then we can apply different tools in order to compare the models. We dug deeper into one of them, looked at one layer, then we look at the distribution that happens in that one layer. And if we want to kind of dig deeper, we can go all the way down to a single neuron in order to look at it. And all of that in an interactive interface that allows you to abstract the different levels. Say we have found one particular model behavior that we want to explain more. We might want to figure out what the model actually cares about. So in a recent collaboration with IBM, we were looking at what context matters when it comes to visual question answering and reasoning. So if we have a visual language model that takes into account a text and an image, can we play around with how the context of the image and the text matches in order to figure out if we give the model a contradictory text and image versus a complementary text and image, how the behavior would change? So our model has a vision encoder, and it learns basically the alignment between text and images to do question answering and reasoning. And what we developed is an interface that allows us to do a lot of different experiments, but for example, perturbing the image and taking away some of the features that might be relevant for the actual prediction, or adding some labels to the image, try to figure out what does the model actually care about in this multimodal setup. And what we create is a data set where we either have a complementary image or a contradictory image to a particular text, and we try to figure out, does the model actually care about the information that is provided in that context, and what type of confusions can we cause in that behavior? We do that for a lot of different domains, and we're trying to really construct this data set in order to allow us to answer questions about the actual reasoning behavior of these visual language models. If you're interested, this will be presented at NeurIPS actually next week, so there's a lot more context where this came from, where we actually try to figure out what is the reasoning that the model gives and whether that actually makes sense in a human perspective and so on and so forth. So this is ongoing work on multimodal explainability. All right, so we looked at workflows, we looked at explainability. Now I want to tell you something about something that I'm personally most excited about, which is how do we adapt human model alignment over time? So how do we guide users over time to basically give us the right feedback, but also how the users prompt the model over time to change its behavior. And there we need to figure out if we can actually predict the intention of the user based on the behavior that they're doing on the screen. And to that end, we actually run a lot of different experiments. So one of them is doing a Wizard of Oz setup where we recruit multiple different users, connect them to the system. We tell some of them that they are trying to guide an AI model. We tell others they are receiving guidance from an AI model, but in reality, they're communicating with each other. And then we can match exactly what they're getting in terms of tasks, or we can give them misaligned tasks and see what types of behaviors arise to try to figure out what is the right context, explanation, and timing of the guidance that the users are expecting. We also implement a lot of different modalities in order to capture the provenance data, so the interaction history that users have when they interact with user interfaces, and then combine all of this into guidance engines that allow us to actually implement co-adaptive guidance interfaces with different strategies. So let's come back to the example of trying to figure out which type of topics are in a particular document. And here we want to learn how do we do that assignment by creating, picking from these different operators that the model suggests or would have actually done if we don't tell it our preferences. So this problem is called contextualized preference learning, and what I'll present is an adaptive guidance interface to solve this particular problem. So in order to represent the documents, we actually represent the history of the documents over here. We represent the model's understanding of the topic distribution over here. We represent the history of the topics over there. And then we add these AI agents. And the AI agents basically give us a verbal and a visual explanation. And they are receiving different user feedback. And their main objective is to learn in which context is it necessary to do that operation that they're trying to suggest. So in your own work, you might have different objectives that you're trying to optimize, and you want to figure out at which point in time do I want to perform a particular operation. In this case, it's combining different topics, but it could be any operation. And the goal of these agents is to basically take one of these objectives and trying to learn from the context of the analysis, when do we do a particular suggestion, and would it be accepted by the user or not? So these agents that we train have different objectives here, and we actually train them on metrics that capture the how good a topic is over time. And these metrics are approximated with these different shapes, and then we kind of capture all of these quality metrics to kind of represent them in different vectors that represent the context in which they learn. So for one particular analysis window, we might know that a particular quality metric, such as the topic coherence, for example, is going up or down. Another quality metric, such as topic separation, is going up and down, and so on. And we represent these into these different shapes. And then we take these shapes, feed them into a model, and then receive a binary suggestion or decision on whether or not we should do a guidance at this particular point in time. So this guidance receives some feedback, and then we can actually train a model. So here's the system running. We have the first suggestion coming in. And you see the agent here is suggesting that we should combine two different topics. So we can take a look at what the suggestion means, and then see, okay, this is the new topic that was created. This is the underlying documents that the agent consulted. And maybe we like the suggestion, so we accept it. There's another suggestion here to split some incoherent topics. So we might want to investigate that, maybe even look at the metrics. And if the suggestion doesn't make sense, we might want to reject that. And then here's a suggestion that we've been ignoring. And we've been ignoring it over time, so it kind of loses confidence. It learns from the non-interaction that this was not the appropriate timing for that suggestion. All right, so with these types of models, we can actually try to figure out what do people actually discuss when it comes to climate change, for example. Do they think that a particular argument was more convincing than another? And if we know that, we can actually take a Reddit conversation over here, train a model to pull apart all of the different threads, and tried to give us some sort of understanding of what was the most convincing argument online when it comes to climate change. So over here, if we actually pull apart all of these components, we can actually take a look at the actual text. And it turns out that people were discussing an article about ice cores that were 800,000 years old, and there are CO2 bubbles trapped in there, and that was a very convincing argument when it came to climate phenomena. So we can take these models and do this down the line, but we can also take the same models and try to train something else. So over here, we're looking at a debate between Trump and Clinton in the presidential debate, and they are talking about taxes. So we're taking some of these trained models, optimizing them for political debates, and now we're looking at them attacking Trump for releasing his tax returns. He said he's under audit for 15 years. Release your tax returns, release your tax returns. And then at some point, Trump will say, okay, fine, I will release my tax returns. So we take these models, personalize them, and adapt them to a particular context, and then we can use them down the line in a very adapted manner. Now, these works, or at least like this one with Trump and Clinton has been a few years old. We actually now are using the capability and the scalability of the large language models to actually do a lot more with that. So I'll show you a collaboration that we did with a company, like the demo is actually just a few days old, where we actually use the same type of modeling. All right.
Thank you for joining us today. Let's start by learning more about the company. What do you specialize in?
We're a B2B logistics provider specializing in supply chain solutions. We work with large retailers and manufacturers to optimize their distribution processes, primarily through warehousing and last mile delivery services.
Interesting. Who are your main clients?
We serve large retail chains, e-commerce companies, and several manufacturers. Our services are tailored to meet the specific needs of these industries.
And how do your clients interact with your services? What are the main channels they use?
Most of our customers interact with us through our client portal, which allows them to track shipments.
All right, so what you're seeing here, and I'll keep the video running, is basically a real-time capture of a conversation between a client and a consultant. And they are trying to figure out what are the different architectures and what are the different services that a company actually provides. So there are all of these layers, from customer layer to experience layer to organization, that the consultant wants to ask the customer about in order to figure out how do they map the structure of what actually exists in that company. So we set up a service where we actually capture that conversation live. We transcribe it, and then we extract the information that is relevant, position it on these different layers, extract icons that represent that, and then put that all together into a structure that would take one of these consultants more than a week to create within the one session live while they're interacting. So imagine now your own applications, your own domains. You probably also have interactions with different people that need to externalize their domain knowledge. And this dialogue augmentation interface allows you to basically do exactly that by extracting the knowledge while it's being spoken and positioning it in the right context. All right. So this is how we do human AI adaptation. And now I want to talk about one of the last steps of this process, which is human feedback. So the question here is, how do we consolidate multiple types of human feedback? And for that, I showed you already this interface where we looked at topic model feedback. We also tried to explain what is the feedback that has been learned by the models, and how do we combine that or consolidate that into one framework. So earlier, I just showed you this particular example with topic modeling. I actually spent way too many years trying to solve the exact problem over and over and over again, but with completely different interaction paradigms. And the goal for this exercise was try to figure out how do we exactly deliver the best learnable feedback from the human to the machine. And what we do in the background is actually try to figure out what has the model learned about solving a particular behavior. So this is a reinforcement learning model in which we take a look at everything that the model learned to decide by itself. Sometimes it takes a particular step and kind of progresses to a different location, but in other times it actually loops around quite a bit. So whenever it encounters a particular problem, it keeps trying to solve it in the same way, and it doesn't actually exit that loop. So we need to optimize these types of behaviors. Right now, we're taking some of this work and applying it also in the context of architecture. So you might know Raphael. He's started his PhD very recently in my group, and we're looking at basically architecture design in hospital contexts, and we're trying to figure out how do we receive the right feedback to deliver the right co-design between architects, medical professionals, and AI engineers, and put them all together. In a similar fashion, PU, a postdoc in the group, also tries to figure out how do we automatically detect different elements in buildings, and how do we walk through interactively and count different elements in construction in order to do that in circular reconstruction and design. All right. So now I've showed you 4 of these areas, and the last one I want to come to is language models, because we are living in the area where everyone talks about language models. And for that, the question that we address are biases and hallucinations, and how do we find and detect them. So with language models, there's a lot of different challenges that need to still be solved. We are tackling that by explaining the behavior of these models, fingerprinting their understanding, and trying to figure out on which data they've learned a particular behavior, and how do we detect and augment hallucinations. So now I want to very briefly ask you what you think a language model should represent. What you see in front of you is the job distribution based on US Census data in the US. So basically, there is a lot more women who are basically secretaries and nurses, and a lot more men who are engineers. And this is the reality of the job distribution on the ground. And now my question to the audience here is basically, what should the model learn? What should we train the model? Who thinks it should be a 50-50 distribution of jobs? No one? Okay. Who thinks it should represent reality? One person. Okay, and the others are don't know yet. All right, so this is what actually happens when we train the model. So there are some distributions that are more or less representing the real world census data, and others where we actually deviate from there. Okay? And the question that I asked you is actually a bit of a trick question. There is no proper answer to that. In applications where we might want to, for example, assess CVs for hiring, we might want to overestimate what this data is about in order to represent an idealistic reality in which everyone can do any job, because we don't want these biases to determine whether someone gets hired or not. In other cases, for example, in medical decision-making, we might want to actually remain with these biases in order to really cater for specific demographics that might be underrepresented in the data. So in every task, we might want different behavior, but it's worthwhile asking, what does the model actually learn? And if we look at the internals of the model, what does it represent throughout the different layers? So in layer 1 of the BERT model, we might look at this distribution of male and female pronouns and see that this model has learned that women are housekeepers, blonde, hysterical receptionists, and men are strong footballers, presidents, and captains. And then one of the questions here is to go through the different layers and see how does that change actually during the training. And then ask ourselves, can we actually get a better distribution that does not separate male and female pronouns as much? So here's another model that was aiming to de-bias that particular aspect. So if you look at this de-biased model, we can go through all of the different layers again and see that the distribution is getting a little bit closer to the diagonal, meaning that we don't have these overly arching characteristics. So we have a larger overlap over here, but then if we actually look at whether this model can distinguish male and female names, we see that it might have unlearned a little bit the concept of gender association to a particular name. So we have removed some of this bias, but while doing that, we have also unlearned some of these aspects that relate to gender. So it's not really clear what we want these models to do, but we can also go a little bit further and try to figure out in a particular context. So here we say, person is great, one could even say that. What should the model represent in that decision making? So we're saying, John is great, one could say that. Jessica is great, one could say that. And then we see all of the different decisions that the model takes. What you see in front of you is a visualization of the beam search tree of the model. So these are all of the decisions that it's making before giving you an answer. And you see already there are lots of biases in there, but we could actually give feedback at these points in time in order to figure out what do you want the model to actually decide when it comes to these types of outputs. So these are kind of things where we reveal some of these biases. And then there's also the problem of hallucinations. So say we ask the model to create a CV of a person. Over here, the model seems quite confident. It's giving us a response where this person was born, who he is, and so on and so forth. But if we go and ask the model the same question 20 times, it would actually hallucinate half of this information. So what we do is we try to extract individual claims from the answer, and we try to figure out would these claims, if we repeatedly ask for the same thing, be consistent through the outcome of this model? So this is called the model self-consistency check. And what we're trying to do is to figure out whether these claims are logically consistent. So this model claimed 12 times that this person was born in 1 year, 7 times that it was born in another year. Using natural language inference, we know that this cannot be true. So we highlight this very subtly over there, just to give a hint to the user that this might be a hallucination that you want to investigate further. So here is augmenting the text output for an end user in order to basically give an understanding of where the model could have hallucinated and where it is consistent. That does not mean that the consistency actually refers to fact, but at least it has been consistent throughout the different generations. All right, so I've taken you on a whirlwind tour through different research areas. If you're interested to play around with any of these tools, again, you can visit our website, and there's a lot of prototypes you can actually try out yourself. But now, to come back to my question about avoiding miscommunications. So how do we do that? One thing is we need to adapt the guidance and analysis processes over time. We need to tailor the interaction workflows that we design for human-AI interaction, and it depends on the different stakeholders, so we need to cater for that as well. We want to combine visual and verbal explanations because that redundancy allows us to be much more clear. And also we need to pick the right metaphors. In some of the experiments that I've done in the past, I refer to our models and their different parameterizations as minions, and we did entire studies where we talked about minions and magic boxes. The surprise here is that for people who are not experts in machine learning, taking that metaphor allowed them to basically overcome the stigmatization of machine learning and so on, and they performed on par with people who actually knew what happens in the background in the model from an engineering perspective. And we publish papers where we describe exactly that phenomena. Actually picking the right metaphor is quite important. All right, so the tools that I just showed you usually take up like a year or so to create, every one of them. It's very, very elaborate to try to create these types of interfaces and also allow them to adapt in real time and give feedback back to the model. So what we're doing right now is taking all of the lessons learned from designing all of these tools, and we're creating what we call our middleware that allows us to break down every one of these processes into individual services that are run on different servers. And basically, for someone who wants to design one of these tools, to come in and just write a config file with a data specification, and then all of a sudden you have one of these tools. This is a project that is currently running, and we want to open source it for everyone to be able to create such interfaces. In the meantime, we're also very, very interested to hear from you what your questions are or what your challenges are for human AI applications. So if you want to send us some inspirations from your own domains, what you would like to solve in terms of human-AI interaction, we're always happy to receive these challenges. For one course that is currently cut out, interactive machine learning, we're always looking for challenges for new student projects. So this is starting every spring semester, where we're looking to actually work on real data and real challenges and so on. And we're starting a new course called Human-Centered AI for Social Good, where we're focusing on climate, peace, and health specifically, and we're also looking to collect challenges. So if this is something that's interesting for you, we're happy to receive that. And to conclude, I asked the question about how we can design effective and empowering communication interfaces for human-AI collaboration. I'm not the first person to ask this question. If we actually go back more than 100 years ago, people were thinking about the same problems. So if you asked people back then how they want to interact with machines, this might be some of the stuff that you would have received. And it's not just interacting with machines in general, but actually interacting with machines in many different fields. So this type of research that we're doing also really lives through the different application examples that we can try it on and the different generalizations that we can transfer from one area to another. And this is why I'm very interested to work across these disciplines to try to figure out how we can bridge all of that. My hope is that through this research, we can actually achieve some sort of seamless human-AI communication and collaboration in the future, because I really, really strongly believe that human-AI teams can solve much more challenging problems than each of them by themselves. And thank you.
Thank you, Menna. Very, very interesting lecture. I just want to open then for a couple of questions. If they're already lined up, or if you want to share already a challenge that you thought of over the last slides, that would be great. And I can pass the mic. I can also, I have 3 questions at least myself, so I can start. A lot of the work in explainability and also in human AI interaction that you showed is anchored in language models, so text predominantly. The fields architecture, engineering, construction, highly driven also by images and 3D models. Do you think now with this middle layer that you are starting as an initiative, those kind of representations would also work with these methods, or new ones are needed?
So yeah, my background has been in explaining text data. So now we're expanding a little bit more into other domains. So on the one hand, looking at multimodality and the kind of interplay between text, images, and other modalities. And on the other hand, like looking at these very specific applications in architecture and construction and so on. So with the 2 new people in the group, that's the hope, is basically to transfer some of these techniques also into these other domains. So I hope if I come back in a few years, I can actually report back on some of these exercises. Yeah.
Cool, thank you. Yes, Russell.
Question that comes up every single time. How do we deal with the fear of AI? We talked about it a bit last week in the industry dialogue. Seems that one of the biggest constraints on implementing AI in any larger and any beneficial fashion is simply the human resistance to significant change, but also that AI presents itself as a different paradigm in our understanding of technology, and one where people, because they cannot understand it intrinsically, it really blocks a lot of the very interesting things that you and your team are doing, and also that we're attempting to do in research.
Yeah, it's a great question. So I think there are multiple facets to that. So one is basically trust calibration. Is like we don't want people to neither over-trust AI, but also we don't want them to under-trust AI. So we want to kind of calibrate that. And it's a very tricky aspect because we still don't understand what leads to kind of calibrating that. So we're doing a lot of these studies, but I think in a lot of fields we need to do that specifically for the tasks at hand, for the models at hand, in order to have some sort of mental model about when can I rely on this and when can I not rely on this. I've been throwing around this idea of an AI driver's license for a while, where basically similar to the process we go through in order to drive a car safely through a city or so, we want to figure out what is the appropriate mental model for someone to use an AI model without them needing to be an engineer, the same we have for basically driving a car. I'm not sure what the appropriate level is and whether it's actually general enough or whether it's very specific to different tasks, but this is an exercise that we're trying to kind of conduct. And then the last part is like basically literacy, like creating different explainability methods and also different articles in order to allow people to educate themselves about AI without having to do a machine learning degree. So I showed in that talk actually a blog article where we're explaining what it means to learn different neighborhood contexts and how does a model actually go about doing that. And we create a lot of these so-called explainers or explorers where you have a blog article using scrollytelling where you go through every different single stage and then see the model's behavior and how that actually translates to a particular aspect. And I think all of these different exercises side by side might lead us to a better calibration and understanding of how we can use AI in the different contexts. So I think the answer is very faceted. And the reason we are also opening up our courses to all of these applications is to try to have feasibility studies on a lot of these different areas in order to cater for the needs of the domains and in order to kind of calibrate with the people together and see how that works for them.
I like your notion of the driver's license, but is it a driver's license or is it training wheels, you know, outrigger wheels on the bicycle?
That's the discussion we have every time, yeah. yeah.
But building trust is different methods for building trust between models and humans. Mm-hmm. Driving license for the model or for the human using the model is also could be in both ways, right?
I mean,
any other questions?
One of the questions we always ask as well is like, how do we open up the human black box, not just the AI black box? And for that, we need to also collaborate with people who have studied that from a human perspective. A lot of the stuff that we do, like these are engineering and technical solutions, but a lot of the questions that we ask, like the one that I asked you about the jobs, is a socio-technical question that does not have one engineering solution, but has actually a lot of societal discourse that needs to happen in order to get there.
Anyone else?
Right. Questions?
I recently heard CEO of Microsoft say that the models that are used in research historically were very different from the models used in production on building products. And with the latest generation of foundation model, this thing is changing. So now researchers and product builders are using very similar approaches, which creates new opportunities. And I think your research is also kind of showing that now synergy or kind of confluence. Do you still, what is your relation to that statement? Do you do a lot of extra modeling work, architecture in terms of AI architecture work that needs to unravel these findings you show, or kind of
I think currently we're at a stage where we need access to a lot of models, but on the other hand, it's very, very expensive to train them, and a lot of companies don't share their models openly. So it's a bit of a challenge to create the types of visualizations that I just showed with the current state-of-the-art models, because we don't have access to their weights and so on and so forth. So some of the stuff that I showed you is basically on open-sourced versions of, or like earlier versions of the current models, just because we need to look into the model to create these visualizations. I have hope that we can solve some of these issues by actually training our own language models and our own vision models and so on through the VISxAI initiative. So we have access to a lot of computing power right now, and we're ramping up to train all of these models. Yeah, it requires all of this in order to actually create this research and in order to explain model behavior and then to be able to judge whether it's safe or not to use in different contexts. Yeah. Yeah, Benjamin.
Regarding the large language models that many of us are working with already, and they are omnipresent, like the biggest players. And from your opinion, how much or how important is and what is the state of the neutrality of those models? Like how much politically colored are they, and how to probably and are there strategies to keep them as neutral as possible? And I would love to hear your opinion about that.
It's a very challenging aspect because I don't think we can actually pinpoint neutrality in different perspectives. There's a lot of cultural norms that are different between countries and so on and so forth. And like literally these models reflect societal biases, and like that's what we just show. A lot of current commercial models have many, many layers on top of the base model to try to be safe. And if I was a company, I would err more towards caution than towards being super free, just to kind of avoid lawsuits and all of that. But of course, it's a developing aspect. Like we need to learn how we use them. The companies need to learn how to use the data and how to provide different interfaces. Many, many things have engineering solutions. But a lot of things need to be discussed, right? We don't know what we need. We don't know what we want in different contexts. Like if you had a magic wand to create a model, what would it do? And I think a lot of people don't have the answer to these questions yet. So I think we need to expose ourselves to these models. We need to create interfaces to interact with them, not just on a verbal level, but maybe also in different other levels to reveal their decision-making patterns. And then at some point, we might have an informed opinion on what we want to engineer. And then I think we are ready to answer such questions. And maybe the answer is that we need different models for different tasks and different societies. But I think at this point, we don't know.
Is there maybe a follow-up question? Is there a way to make the human tuning of these models transparent, that it can be, that me as a user can see, okay, here, this is an answer that is highly tuned by human feedback already from, or?
I think like this would be a really good desire, and I think people are working towards that. Some of the stuff that I showed you, for example, with the beam search tree, this generator explainability method, we can capture all of this data. So like the provenance data that is generated through the interaction, we can capture that and reveal that later. But of course, this is a very limited interface in terms of how many interactions we can capture. If you want to do that at scale, we need to figure out how do we actually scale that up. It would be really interesting to do that, but I have not seen any work so far, at least, that can provide this. But I think people are working very actively on that, and like there are large communities behind this, so I'm sure it's moving very, very fast towards maybe achieving some of these goals. Yeah.
Yeah.
Yeah. Hey, thanks for the talk. As a follow-up question, sort of to the one before, I was wondering if there's ways to sort of proof the models that are open source from misuse. Like you gave the example how you learn from what answers work on climate change and convincing people about it, but the same could be used for misinformation and what kind of catchphrases used for climate change deniers or targeting for like really misuse in political purposes and different agendas. So is there a way to sort of proof for this sort of things happening?
I mean, there's a lot of efforts to watermark outcomes of these models to be able to kind of identify them. I think a lot of times when we come to things like fact-checking and like misuse and so on, we need to regulate maybe the use cases themselves rather than regulate the models. So you could have one model trained on biological data that can be used in both creating new medicine, but also biological weapons, the same model. And you can try to regulate cases by law to say, okay, like it's not allowed to kind of use this model for this and this case, but then you need a way to prove it and reinforce it as well. The other aspect that I've heard in this context is basically you also want to figure out a way to actually watermark real human data. So right now we're getting more and more data from these models onto the internet and onto different data sources. So at some point it will be really difficult to actually distinguish the actual truthfulness content of different data that we see and like the different things that have been generated and hallucinated by different models. So we need to figure out a way to actually watermark what has come from a real truthful source and what has been generated by a model, whether it's like intended to be misused or whether it's unintentional but still kind of misguides users. So I feel like this is an ongoing discussion right now. There's a lot of the tech companies are working on model safety, but I have not seen a conclusive answer to these problems yet. Yeah.
Thank you. I think we can close it here. I guess everyone is also looking forward to more informal discussions at the apero. Thank you, Menna. Join me in thanking Menna. And I just also want to bring your attention to next week's, the final talk for this semester's seminar series. It's from Brent Chamberlain, who is a guest at the LVML, the lab for the Large Scale Virtualization Modeling Lab, and he will talk to us about a research project that they have done over the last couple of months in that visiting exchange. And now, let's enjoy the apero.